pleasure to welcome you all to this virtual event hosted by the Institute France. I'm Robert Dijkgraaf, I'm director of the Institute, and I'm absolutely delighted that we have Leah Medeiros here with us, actually in her office on campus, which is very good. So, she is an NSF Astronomy and Astrophysics postdoctoral fellow in the School of Natural Sciences at the IES, and that these are these national fellowships which are at the very highest level for young scientists. Leah is a native of Brazil. I didn't know that actually, and she earned her bachelor degree in physics and astrophysics at the University of California, Berkeley, and then went on to Santa Barbara, where she earned both her masters and PhDs. As she also held an NSF graduate research fellowship and used that to conduct the majority of her dissertation research at the University of Arizona Stewart Observatory. And she also spent a year at the Black Hole Initiative at Harvard, which is one of the centers of black hole research. She is a lead in the famous Event Horizon Telescope Working Group. That was the collaboration that made world news, I think on April 10th, if I remember well, in 2019. The one of the few cases I like to say when a piece of positive news was on the front page of basically any publication in the world. And this was absolutely breakthrough moment in science. I think it was the height of 2019. I think it's one of these rare 5-star discoveries, which we're actually very lucky to have had in the last decade. She's a very active member of that group and published just some new paper that she might be talking about how this image is much more than an image, but it's also a way to test Einstein's theory of relativity. Now, as I said, her work has been recognized many times. We just said that the Event Horizon Telescope result won the Breakthrough Prize. But, you know, she has also received the Chair's Service Award at UCSB at Santa Barbara for her work with women in physics. The 2019 vote of applause of the Brazilian Senate. That sounds absolutely lovely.
He invited me to the Senate. It was very fun.
It's a rare honor, and you. It was also, of course, as I said, the Breakthrough Prize. Now, Leah has also been tremendously active as her, in her career, starting as an undergraduate in outreach. At Berkeley, she was part of COMPASS, which is a student-run organization dedicated to fostering creative, diverse, and collaborative community in the physical sciences. Very necessary, I would say. She has mentored both undergraduate and graduate students, and in particular was very instrumental in leading efforts to encourage women to pursue STEM careers. At both UCSB and Arizona, she planned and led outreach projects for exciting physics topics to high school students. And I would say there's no lack of raw material in your field to reach out. Actually, currently, here in Princeton, Leah is partnering with the Princeton Children's Fund, which is a nonprofit organization focused on closing the achievement gap for low-income students, to run an after-school program and a summer program to teach middle school students astronomy and basic programming. And she's also planning to make a curriculum on that. So, Leah, you're incredibly busy. You're a cutting-edge scientist. You're a great advocate for your field. And among all these many duties, you also find time to speak to us. So it's delightful to welcome you here tonight. And I would say the screen is yours.
Thank you. Thank you so much for that really wonderful introduction. I think that's the best introduction I've ever had. Let me just share my screen really quick here. Okay, so as Robert just told everybody, I will be talking about the Event Horizon Telescope, and specifically about how this is not just a really fun, exciting project where we can make an image of a black hole, but how this is actually a really cool test of gravity. And I'm going to be talking about how we can test gravity in general with this experiment, but also specifically talking about a paper that just came out just a few weeks ago. Before I move on from my title slide though, I do want to explain to you what it is that you are all looking at here. So I work a lot with simulations. So what you're seeing is the result of a simulation. And what we do with these simulations is we evolve or simulate what happens to plasma as it swirls around a black hole. So these simulations take into account the fact that the plasma is going to be affected by the gravitational field of the black hole. It also takes into account how the charged particles in the plasma will interact with the magnetic field of the black hole. And what you will see here, this turbulence that you see in this swirling matter here, that comes from the interaction of the charged particles with the magnetic field. And that's actually what makes matter fall into black holes. And after we simulate what happens to this plasma, we also have to ask ourselves, or in this case, ask the computer, what happens to light, right? So we as astronomers, we observe light that this plasma emits. And so we have to also simulate whether or not this plasma would be emitting light, whether it might be absorbing light, what wavelength it might be emitting at, and also how the path of the photons will be affected by this black hole. So all of that put together, you get something that looks like this. And this is a free color image where the blue that you see corresponds to light that has a wavelength of 1.3 millimeters. And that's the wavelength that the Event Horizon Telescope observes at. There's also a green emission that is very similar to the blue emission. So really you're probably just seeing like a bluish green color. The green emission is wavelength, that wavelength is 0.87 millimeters, so it's a bit shorter. And then red is a really long radio wavelength. And that's really showing you this really large scale structure that moves off towards the right. And that's really this huge jet that we expect this black hole to have. So we're going to be seeing a lot of these simulations. So I just wanted on the very first slide, just explain to you what it is that you're actually looking at. So today we're going to be talking about testing gravity. Specifically, we're going to be talking about testing Einstein's theory of gravity, which is called general relativity. So I always really enjoy the fact that I'm testing general relativity in the same institute where Einstein himself worked. So that's always really fun. And I specifically just wanted to highlight a few aspects of this theory and really contrast it to Newtonian gravity. So according to Einstein's theory, gravity is actually not a force, but rather it is a geometry. So it's a geometric effect. And so what that means is that we need to take into account the fact that we live in not only a three-dimensional space, but we're also moving through time. Okay, so according to general relativity, we need to treat time and space as part of the same thing. And so what actually happens, what we perceive as gravity, is actually the fact that mass will curve this thing called space-time, this four-dimensional space. So unfortunately, I can't draw in 4 dimensions, but I've made a very simple diagram here that's just 2 dimensions. I've compressed all of the free spatial dimensions into 1 dimension, and right now you're just looking at flat space-time. And now I'm going to add in a mass, and we're going to see how this mass will warp or curve this space-time. And what's really interesting is that mass will curve space-time, and then the curvature of space-time tells mass how to move. And the idea here is that you can think about it as if you had a small planet orbiting around the mass that you see here. That planet is going to try to move in a straight line, but it's not going to be able to move in a straight line because it's constrained to move through this really curved space-time. And so as an analogy, you can think about yourself moving on the surface of the Earth, right? You can try to make the shortest distance between 2 points. You can try to walk in a line, but because you are constrained to the surface of this curved sphere, you won't actually be able to walk in a straight line, right? So no matter what you do, the shortest distance between 2 points will still have a slight curve in it because you are moving through a curved space-time. So this is the same thing that happens to matter. And what's really, really interesting about the theory of general relativity when you compare it to Newton's theory of gravity is how these 2 different theories predict whether or not light will be affected by gravity. So according to Newton, light should not be affected by gravity because light does not have a mass. However, according to Einstein, light should be affected by gravity because light will still have to move through a curved space-time. And so I have also a second diagram to show that. So I've now added these red lines. These red lines are photons, and at first they will go in straight lines, but then we're going to add in a black hole, and we're going to see how that will affect the trajectory of these photons. And as you can see, some of them even fall into the black hole. And so because these two theories predict different behavior for light, we can actually use that to test which one of these theories is correct. So I have a diagram here, which I hope you can see my cursor. I know it's a bit small, but we are down here on Earth, and the sun is this big orange sphere here, and there is a distant star right there. Hopefully you can see that there's other little more distant stars behind that one. And so I'm going to describe here an experiment for how you can measure whether or not the presence of the sun will affect the trajectory of light. So when the Earth is over here on its orbit, we can measure the position of this star relative to these other distant stars. And then we wait a few months, this Earth will come around the sun, and then you can measure the position of this star from our perspective again. And what happens is light that is coming from this star, as an example, there's this yellow line here, it's going to go in a straight line as it's moving through flat space-time. However, when it gets close to the sun, it's going to be moving through a region of space-time that is curved. And so it will have this deflection that you see here, and then it will come to the Earth. On Earth, we always assume that light has moved in a straight path, right? So if we receive light that's coming from that direction, let's say, we're probably going to assume that there's something in that direction that's emitting light. And so what that means is that we're going to trace this line all the way back in a straight line, which is shown by this gray line here. And so we will measure the position of the star as being over here, when really the position of the star was here. And so this experiment was done over 100 years ago. So it was the actual experiment, the actual observations were done on May 29th of 1919. And the image that you see here is one of the original images from that experiment. And it's probably doesn't look like great quality, but you have to keep in mind that this was done with photographic plates over 100 years ago. And what you've probably noticed is that you can't really see the sun, right? The sun seems to be blocked. That's actually a really important part of this experiment. You need to wait for a complete total solar eclipse to be able to do this experiment. Otherwise, there will be way too much light from the sun and it will completely wash out the rest of your image and you won't be able to see light from these small stars. So in each of these white circles, there are really small stars. Again, it is very hard to see. I think the easiest to see might be this one right here or that one. And so a few months after taking these observations, they actually used rulers to measure the location of these stars relative to everything else. And this was the front page of the New York Times the day that the results were published. And it says, "Lights all askew in the heavens, Einstein theory triumphs." And that's what really made Einstein so famous. And so you might be wondering why we are still trying to test the theory of gravity, right? So I just said that the first time that we tested the theory of gravity was over 100 years ago. Why is it that we are still trying to test the same theory if we've been testing it for 100 years and we've never been able to prove it wrong? Well, there's a few different aspects to this question that I'm going to try to explain here. So the first thing to keep in mind is that when we say we are testing the theory of gravity, there are many different aspects of the theory of gravity that one could test, right? And different experiments will probe these different things, and some of them are easier to test than others. The other thing, other aspect of this is you need to keep in mind whether you are probing the gravitational field in a really strong regime or in a really weak regime, right? So for example, I have here an animation where I've ordered the strength of gravity for 3 different experiments. So the first few experiments we did were in the solar system, as example with the solar eclipse, but there are other experiments as well. So I would classify this as a medium strength of gravity. The sun is massive, but it's not as extreme as a black hole, for example. And then we've also been able to perform tests with cosmology. And so if you're not familiar with cosmology, cosmology is really just a study of the universe as a whole, right? So we're looking at really, really large scales. And in cosmology, when you do a test of gravity, it's going to be a very weak gravitational field because on those scales, the universe is mostly flat. And it's only recently that we were able to really probe the strong gravity regime with black holes. And the first time we were really able to do that was with gravitational wave observations just a few years ago. And now we're also able to do it with the image of the black hole. So obviously I'm going to be talking a lot about black holes. So I do want to give you a few of the basics. So first, I'm going to define black holes as a region of space-time where the gravitational field is so extreme that not even light can escape, okay? And what makes black holes so special, what makes their gravitational field so extreme is actually density, okay? So that's what really matters. If you want to make a black hole, it's not that you need extreme mass or you need it to be made from a specific type of matter, but you really just need it to be really, really, really dense. And with extreme density, you'll get extreme gravitational field or extreme curvature. And so as an example, if you are wondering what I mean when I say extreme density, if you wanted to make a black hole out of the Earth, you would have to have the whole Earth squeezed so that it was about the size of a marble, and it would look like this. So obviously, us humans will never be able to accomplish this. Obviously, we also don't want to accomplish this. We'll never be able to make a black hole on Earth. But there are many reasons why trying to study black holes in space is really what I like to call the best laboratory to better understand gravity. And so a couple more vocab things that we need to get through. So the size of the little Earth that I'm showing you here, this is actually the size of the Earth's event horizon if you were to make a black hole out of the Earth. And the event horizon is essentially the boundary between the black hole and the rest of the world. And if you remember my definition, which is that a black hole is a region of space-time where the curvature is so extreme that not even light can escape, what we actually mean when we define this event horizon is really just a distance, okay? So we're really just saying, if you are so close to the black hole that you are closer than this distance, then nothing can escape the black hole, not even light, okay? But it's not really a surface, right? If you were to cross the event horizon, you wouldn't actually bump into anything. The other thing to also discuss is what happens inside of the event horizon, right? So if I just told you there's no surface, so what actually is inside of the black hole? Where is the mass of the black hole? Well, what happens is all of the mass from whatever existed before the black hole collapses into an infinitesimally small region, and we call that a singularity. And so one of the reasons why black holes are such incredible laboratories, in my opinion, is the fact that they're really, really wonderful for us to understand how these two different theories that are really important in modern physics interact with each other. So we've already talked about the theory of general relativity that explains how gravity works, but there's this other theory that's also really important in modern physics, and that's the theory of quantum mechanics. If you're not familiar with quantum mechanics, for this talk, you just need to know that quantum mechanics describes the behavior of really small things, okay? And so we want to understand how these two theories will interact with each other, but it's really hard to make an experiment to test that because you would need an object or a phenomenon where you really require both theories to explain that object or that phenomenon. And black holes are really the perfect thing to do this because, as I've already explained, we have very extreme gravity. And because all the mass is in this singularity, we also need to understand what happens to really, really small things. Okay? And so this entire talk is going to be talking about how we can actually perform an experiment with a black hole. And obviously this is really complicated because we can't just, create a black hole on Earth. We also can't send any probes to a black hole like we do with Mars, for example. And so to actually be able to use a black hole to perform an experiment, we need to be really kind of clever and think outside the box a bit. So what we're going to do in our experiment with the EHT is we're going to use the same principle from that very first experiment that I explained to you, but instead of the sun, we're going to be using the black hole. So the idea is we want to learn more about the curvature of space around a black hole. And what we're going to do is we're going to study light that has moved through that curvature. And so the same way that we studied the light that moved through the curvature of the sun, we're going to be studying the light that got really close to a black hole and had to move through this curved space-time. And so people have been wondering what you would see if you were to look at a black hole for many years, since the 1970s. The image you see here is actually from one of those original publications. And what they calculated in this publication was what you would see if you were to look at a black hole, and if there was somebody behind that black hole shining a flashlight on it. And what they found is that you would see a bright ring that would encircle a dark region. And that dark region is what we like to call the black hole shadow. An easier way to think about it is that the black hole shadow is the shadow that the black hole casts on the surrounding emission. So the light that we actually observe comes from that plasma that's going around the black hole. But there's going to be a region of missing light because of the black hole. So obviously, since the 1970s, we've made a lot of advances. We have a much more detailed understanding of what an image of a black hole should look like. And I wanted to take this opportunity to show you specifically what feature on this simulation denotes the edge of the black hole shadow. And so if you can see this bright white ring here that remains completely constant as everything else changes, I'm going to highlight it in this black dashed curve here. That is the edge of the black hole shadow. And what's really, really interesting is that if general relativity is correct, we know exactly what the curvature of black holes should be. And if black holes have that curvature, then we know exactly what the size and the shape of the black hole shadow should be. We know it's going to be a circle. The asymmetry is very, very small. We've constrained it very well. And we know that the size is only going to depend on the mass of the black hole. And since these black holes are far away, it will also depend on the distance between us and the black hole. And so the experiment really is as follows. We have a prediction from the theory of general relativity for the size and the shape of the black hole shadow. We have black holes in space where we have measured the mass of them and the distance between the black hole and the Earth. And so we know exactly what size ring we should have in our image. And if we have something that is consistent with general relativity, that's great. And if we have something that is not consistent with general relativity, then we're going to have to rethink how we understand gravity and black holes. So for those of you who perhaps are interested in a bit more details of what the black hole shadow is, I just wanted to include this diagram here. It's a bit more technical, but I won't spend too much time on it. So this is a diagram. Here in green is the event horizon, and this dashed line is what we call the photon orbit. This is just a distance from the black hole where it's possible for light to go around in a circle. And all of these blue and red lines here on the right, these are all photons. And so we're going to see the trajectory of light as it moves towards the black hole. These are results from a simulation. And so as you can see, all of these blue photons are going to fall into the black hole. All of the red photons will escape to infinity. And a cool way to think about this is you can make an analogy with an impact parameter, if you remember impact parameters from your E&M classes or anything like that. So what we call the black hole shadow is really this whole region here, denoted by these blue photons that fall into the black hole. And so I wanted to emphasize that the black hole shadow is much bigger than the event horizon. It is very different from the event horizon, and you can create a black hole shadow without actually needing an event horizon, which is kind of interesting. So now that we've talked about what the black hole shadow is, we also need to talk about what conditions are necessary for us to actually be able to observe the black hole shadow of an astrophysical black hole. So first, you need enough light to actually illuminate the black hole. The black hole does not emit any light that we can observe. So the light that we see is coming from this plasma, so we need to have enough light around it so that we can actually observe something. We also need the emission to originate close enough to the black hole so that it is gravitationally lensed around it, but far enough away that it won't just fall in. And finally, we also need the surrounding plasma to be transparent so that we can actually see all the way down to the black hole. So the simulation you're seeing right now, this is a wavelength this is light that has a wavelength of 1 centimeter. So it's a fairly long radio wavelength. And at that wavelength, you can see these yellow structures that are the jets of the black hole, and you can see this orange donut, which is what we call the accretion disk. This is where all that plasma is swirling around. At this wavelength, you can see this, big orange donut, but you can't see through it to see the black hole shadow. And so you can make an analogy here with X-rays, right? So with humans, we view the world in visible light. We can't see through our skin. But if you need to make sure that your bones are healthy or that you didn't break anything, you go and you get an X-ray. So you go to a much shorter wavelength, and that shorter wavelength can pass through your skin and through your muscles so that they can see what's happening with your bones. And so in the same way, we're going to go from 1 centimeter all the way down to 1.3 millimeters, much shorter wavelength, and we'll be able to see through this disk. You'll see how as you go to shorter wavelengths, it just becomes transparent. We can see right through it. And this region here is the black hole shadow, this whole area here. So most of my talk is very theoretical and very focused on the gravitational aspect of this, but I did want to just take a little bit of time to talk about the experiment as a whole. So I'm going to take you on a tour of all of the telescopes that participated in the observations of 2017. And those are the observations that were used to make the image of the black hole in the center of M87 that you saw in April of 2019. And so I just want to emphasize that this is a worldwide array of telescopes. There are over 300 people involved in this project. A lot of different people working on a lot of different aspects of this. And obviously I'm focusing on the aspect that I myself work on, but there's a lot of other really, really exciting and really interesting science that is happening in all these other aspects. So we used all of these telescopes spread around the world and a lot of really complicated algorithms to create the image that you saw in April of 2019. And so as you can see, it is in fact a ring shape, right? So we can measure the diameter of this ring, and we can ask ourselves whether this is consistent with the predictions of general relativity or not. And the first answer is that yes, it is in fact consistent with the predictions of general relativity. And then the second thing we wanted to do is we wanted to know, okay, how restricting is this, right? So I say that it's consistent with general relativity, but how much wiggle room do we still have? How different from the predictions of general relativity could a black hole shadow be and still be consistent with our observations? And so we define an error bar where the size could be what is predicted by general relativity plus or minus about 17% and still be consistent with our results. And so this is what we had accomplished in April of 2019 with those first publications. And then what we've been working on since then, specifically with the paper that came out just a few weeks ago, was going one step further. So now that I've said, okay, this black hole shadow is consistent with what's predicted by general relativity, I want to ask the next question, which is, okay, how strong are these constraints? Have I ruled anything out that wasn't already ruled out? by previous experiments? Am I probing a part of the theory of gravity that has been probed before, or am I not, right? What aspect of the theory of gravity are we really probing, and how does this compare with other experiments? And so one of the things that I've been working on during the last year that I've been at the IAS is asking myself, or asking a computer, what happens if you change your black hole? So the idea here, you can think about this very geometrically. You start with the black hole geometry that is predicted by general relativity, and you change it. You add a modification, or you add a perturbation, or you change it in some way. And what I've been doing is running simulations for what the black hole shadow would look like if you change it in different ways. So over the last year or so, I ran about 24,000 simulations for different black holes. These animations that you see here are just a couple examples from those simulations. This blue circle denotes the edge of the black hole shadow. On the right, you can see that I'm changing a modification that changes the size of the black hole shadow significantly. On the left, you see that I'm changing a modification that changes the shape significantly. So it's almost a half circle. And if you're interested, you can go on my website, leamedeiros.com, and I have an interactive plot where you can actually change these different perturbation parameters and see their effect on the black hole shadow. And so we then compared these 24,000 simulations to the constraints from the EHT observations. And so I'm summarizing these constraints here. This black circle, solid circle here, this is the size and the shape of the black hole shadow for a Kerr black hole, for a black hole that is consistent with the predictions of general relativity. And the dashed lines are the boundaries. So anything that's within these boundaries is not ruled out yet. Anything that is outside of these boundaries is ruled out. So the red ones are ruled out, the green ones are not ruled out. And so we place constraints on different modifications to the black hole geometry. So this is really exciting, and we were already very excited at this time, but we wanted to go one step further and ask ourselves, okay, how do these constraints on this geometry compare to other tests, and how do we know what aspect of the theory we are testing? So we were able to show that the aspect of the theory of gravity that we are testing is the same aspect of the theory that is tested when you measure the precession of Mercury around the sun, for example. And so that's really exciting. So Mercury's orbit precesses, as you see here. This is obviously exaggerated so that you can understand what's happening, but this is something that we've been measuring, we as humans have been measuring for many, many years, and we've used this to constrain this particular aspect of the theory of gravity. And what we were able to do with the image of the black hole, even though the error bar is about 20%, because we are looking at a black hole and because the gravitational field is so extreme, our test is already 500 times better than what can be done with Mercury in the solar system. And so that's already really exciting, especially when you take into account the fact that this was just the very first image that the EHT published. And so in 2017, we only had 6 telescopes. In 2021, we hope to observe with 9 telescopes. And so we hope to bring that error bar down significantly, and we'll hopefully be able to have even better tests. The other aspect of this that's also going to be improving is that we've only imaged one black hole so far, but there is another black hole in the center of our own galaxy that we also want to image and also use to make a second test of gravity as well. The other thing we were able to do was to compare these constraints to the constraints that you can get from gravitational wave detections. And so I don't have enough time to really go into the details, but we are probing slightly different aspects of the theory, but we are similar enough that we are able to compare to each other. And what we find is that the image of the EHT is actually probing this particular aspect of gravity at about the same level as gravitational wave experiments, which is super exciting because we are actually looking at very, very different black holes. So gravitational wave experiments look at small black holes, so there are, a few times the mass of the sun. But with the Event Horizon Telescope, we look at black holes that have a mass that is equal to either 1 million or 1 billion times the mass of the sun. So we're looking at much, much bigger black holes. So it's always good to test even if you're testing the same aspect of the theory, testing it in different regimes is always important, as I mentioned. So that's also super exciting that they're comparable, but still complementary to each other. And we hope to be able to join these two constraints in the future. And so with that, I will just tell you my summary. So the first thing is that black holes offer an unprecedented opportunity to test the theory of gravity, and we're currently in a really, really exciting time in history to be able to do that. So you've all been living through a really big change in black hole physics, because just a few years ago we'd never been able to probe the space-time around the black hole. But with gravitational waves and now with this image of the EHT, it's a completely different situation that we can really use black holes as a real experiment. And so we've been running tens of thousands of simulations of how different modifications would affect the size and the shape of the black hole shadow. And we use these simulations together with the measurements from the image of M87 to constrain what kinds of modifications are still allowed. And finally, our constraints are already 500 times stronger than what can be done in the solar system, and they are comparable to gravitational wave constraints. And with that, I will take any questions, and thank you all for listening.
Thank you, Leah. I'm just applauding on behalf of all of us. And indeed, beautiful images. I'm sure there are many questions, so you can just unmute yourself, speak up, raise your hand. And use the chat function, whatever Zoom allows.
I can't see the chat, so if anybody's in the chat, can you?
I saw Bob Fernholz, so please unmute.
Yeah, that was very interesting. So did you say that the mass in a black hole is all concentrated at the singularity?
According to general relativity, there are a lot of people that are currently working on understanding whether or not that's actually the case, or whether the theory of quantum mechanics would change that at all. And that's one of the big things that we would love to be able to understand more with regards to black hole, is whether the prediction of general relativity that you would have all of the mass in an infinitesimally small space is actually realized in the universe or not. Sorry.
And so how do you,
did that answer your question, or?
How can you check that? You can't see inside the black hole.
Very good question. Yes. So by definition, no information can escape the event horizon. And so we will never be able to actually probe anything in the event horizon. But the idea is that, at least from my perspective, I think that learning more about how black holes behave in general is the right direction to go to understand how these two theories interact. And so there could be, for example, hypothetically, let's say that quantum mechanics fundamentally changes black holes in a way that you could measure outside of the event horizon, right? Let's say that it, for example, can change the shape of the black hole shadow. Then if we were to observe that, we might be able to come up with a new theory that would explain this new phenomenon that we see, and that new theory might predict something different for the inside of the black hole. Does that make sense? Even though we can't probe the inside of the black hole directly, by probing what we can, by probing as much of black holes as we can, we might already find something that's different from our expectations that might lead us to change our theories, which would then affect our understanding of the inside of the black hole. Does that make sense?
No, that's fine. I understand very little about black holes, so I mean, it's
okay.
a question. Yes.
Thank you for your questions.
If we just speak up, this is David Roundtree.
Yes, go ahead.
So one of the parameters that you needed to predict the size of the ring was the mass of the black hole. And I was curious as to how that's measured and how dependent on theory the measurement is, and how much it's considered essentially just to be locked down.
That is a very, very good question. And this is something that I would have loved to include in here if I had the chance. So the black hole that you've all seen a picture of, that black hole is in the M87 galaxy, and it's about 55 million light years away. So with a black hole that's that far away, what we can do is we can try to essentially use a lot of statistics to estimate how fast we think stars are moving around it. So let me just, I'm going to change the order of how I was going to say this. So first, actually, let's talk about the black hole in the center of our galaxy. So that black hole is much closer. And what we can do with that black hole is we can measure the location of specific stars as they move around their orbit around this black hole. And this is actually the experiment that just won the Nobel Prize just a few weeks ago, is measuring the orbit of these stars as they go around the supermassive black hole in the center of our galaxy. And so you can measure these orbits of these stars and use that to measure the mass of the central gravitating object in the same way that we use the orbit of the planets around the sun to measure the mass of the sun many years ago. So this is the simpler version. And then M87 is the more complicated version because we can't actually disentangle individual stars because they're too far away. But we use the same principle of what we see when we can disentangle the location of each star to measure the mass, but we do it in a more statistical way. So the error bars are larger. But essentially what happens is we can use specific signatures in the light that we receive from the galaxy to estimate kind of what the average velocity of stars is in that region at the center of the galaxy. And then we can use the average velocities of these stars to have an estimate of the mass. And so the error bar will be bigger than what we get with the black hole in the center of our own galaxy, but the 20% error bar that I quoted includes the error bar of the mass measurement.
Okay, thank you.
Yeah, thanks.
Further questions? Carl, do you have a question? No? Leah, I was wondering myself, in some sense this whole project started by looking at the biggest black hole you could find, right? So if you look at the future, other black holes will be more distant, will be smaller.
I have a plot for you. Hold on. I hope I can find it. It's in here. Yep. Ha, that was really lucky. Okay. Sorry. Continue asking your question, but this.
Yeah.
plot
So I was wondering,
will answer your question.
what are your expectations of the future? Is it more exciting to get to know these other black holes, or is it more exciting to study in greater detail these big black holes in our galaxy in an M87?
So both things are very exciting, and the EHT is working on both. So this plot here on the right is a summary of a bunch of different black holes. And what this plot is showing you on the y-axis is how bright they are at 1.3 millimeters. So we want things that are at the top of this plot because that means they're bright enough that we can actually observe them. Otherwise, they're too faint, we can't get enough light, we won't see them. And then the x-axis is showing you the resolution that the EHT could achieve. And so things that are more towards the left will appear bigger, will have better resolution. Things that are towards the right will have lower resolution. So the two black holes that we observe are these two in this red square here. And so they're very clearly outliers in both that they are bright enough and that they are big enough in the sky that we can observe them. However, all of the black holes in this purple triangle here, we won't be able to see the black hole shadow for these black holes, but they are bright enough for us to observe. And there's actually another one that's up here that didn't even fit on the plot because it's so bright. And so the Event Horizon Telescope is essentially observing all of the black holes in this purple triangle as well, but the science goals are different, right? So I didn't focus on those black holes for this talk because you can't perform tests of gravity with those because you can't see the black hole shadow. However, they are super interesting for a lot of other scientific questions, such as explaining what causes these jets. So I didn't talk about this slide, but this is a picture of M87. So the black hole is way down there, but this big blue structure that you see here, this is this huge jet. And we have a lot of theories to explain how these things are created, involving magnetic fields and charged particles interacting in such a way, and maybe it's similar to what causes like the aurora borealis on Earth. Maybe it has to do with the spin of the black hole itself. Like we have all of these theories, but there's still a lot that we haven't really been able to test about how these jets work. And so these black holes in this purple triangle we hope will be really, really interesting from that perspective. And there's also some speculation that one of these black holes might actually be a binary supermassive black hole, which would be super, super interesting because there's this upcoming gravitational wave experiment that is going to try to observe gravitational waves from supermassive black holes, LISA. And so if we could, probe a supermassive black hole binary and then, send that to LISA so that they can potentially observe that, that would be really, really exciting as well. So it's kind of both, right? So we're trying to essentially do both things. We're going to try to continue to observe the two that are the biggest so that we can get better understanding of those two. There's a bunch of different ways in which the actual experiment will be improving over the years, but we're also going to be studying these other ones as well.
Thank you. Any other questions, remarks?
Yeah, Robert?
Yes,
am I
Carl,
audible?
go ahead.
Yeah, to follow up on Bob's earlier question about is all the mass in the singularity? I'm just wondering, how might it be possible to be otherwise? I thought it was an irreversible collapse down to nothing. What's the speculation or conjecture as to what it might be other than a singularity?
So I can definitely try to answer this, but I will say that that is a bit outside of what I actually work on. I have friends that work in that field, but it's not actually what I focus my time on. I think Robert actually might have a better answer to this than I do. But some of the work that I've been seeing other people do is, for example, ask yourself, quantum mechanically, will quantum mechanics step in and not allow you to create this really, 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 really small thing? Will instead you have something that has a non-zero mass, right? So this is like the simplest way to do this. And the reason I know this is because from a numerical simulation point of view, this is something that I can actually simulate, right? And so this is probably the dumbest way to treat it, but it's the only way that I know of that we can really simulate these things, is instead of having a infinitesimal point at the center, what would happen if instead you had some sort of object inside of the black hole that has a non-zero radius? Would there be any observational effects from that? And so we can run simulations of that kind of thing and then change the size of it, change, maybe it will have some sort of reflection. So not all of the light would fall in, maybe part of the light would reflect, and we can play with those kinds of things. But as far as like a complete theory that would self-consistently predict something else, I can't really fully answer that. I think people are still working on it. I don't know, Robert, do you agree with that?
I think you put it marvelously, and I think Carl, of course, many of our quantum gravity theoretical physicists are working exactly on these issues. I just want to add one more point, that the physics of what happens in the singularity, although it's hidden behind the horizon, it's very similar to the physics what happens close to the Big Bang, which of course is not hidden by the horizon. So we think that anything we can learn in the context of black holes has kind of a mirror image in terms of understanding cosmology and cosmological observations. So in that sense, it's a fundamental question that is basically in a black hole time ends and in the Big Bang time begins, and for both equally mysterious, but the two fields are very closely related.
All right, thank you very much. Thank you both.
I don't have any other question, but I also want to ask you, Lee, because you do a lot of outreach and so I'm just wondering, whether the image, the famous image that was produced by the EHT, did that change? I mean, have you observed, so to say, in your interaction with other groups, whether children or outreach, that people were triggered by that result? Because it was, there's something very nonlinear in which you communicate science. If you get at a certain level, then certainly it spreads around. So
yeah, that's
I know you're partly
really
responsible for
interesting
producing it, but have you also observed the effect?
That's super, super interesting. And I have so many things to say. Where do I even begin? So I'll just start by saying that in 2019, I gave 27 talks. That is not normal. That is not really healthy. But it kind of goes to show that, the level of interest just went from maybe 8 talks a year to a really extreme number because it was more than, once every 2 weeks. So there is obviously more interest both from the scientific community and the public. What I think is really, really interesting to really think about, though, is why is it that the image provokes such a different response from all these other tests, right? Because we as scientists, we've known that black holes exist for quite some time. We've been measuring the mass of the black hole in the center of our own galaxy very precisely for a long time. There's nothing else that we know of that could be that massive in such a small space, right? And so for us as scientists, the fact that black holes existed was something that we've known and accepted for a long time. But I think it's really, really interesting because the image, like the public's reaction to the image, it feels like this is the first time that a lot of people really believed that this is actually real. And so I think that that's what created such a big public response, is that for many people, this was the first time they believed that black hole is a real thing, right? And that's not, the EHT didn't prove that, right? Like this has been known scientifically for a long time, but for the public, when you tell them, oh, we've measured the mass of this thing because we see the orbit of these stars, it just doesn't have the same effect of, here's a picture of it, that's it, you know what I mean? And so that's been really, really interesting to see kind of the psychology of how, we as humans interpret different scientific results. And, so many people, so many like members of the media have come to me like, oh, you guys discovered a black hole. And it's like, well, no, we knew it was there. That's why we looked, we knew so much about it that we were able to build an instrument that was perfect for this specific thing, right? We knew exactly how big it was going to be. We knew exactly what wavelength to use. We knew where it was going to be located. We knew the distance. We knew everything about it, which is why we were able to do this. We didn't, discover the black hole. But it's just been really, really interesting because, how humans perceive science is super interesting. And it really does seem like, an image is still worth a lot more than words.
Thank you. There was another question here in the chat. How do you know that you're using the right constraints in measuring the accuracy of your?
In what? So I think this is a really interesting question, but there are many different ways that I could potentially interpret this question. So there are many different constraints that come into play here. So there's the constraint that comes from the mass measurement, right? So we have a mass measurement that has an error bar. And that's something that was done years ago by a different team. And we trust their error bar based on reading their paper and them explaining to us where that error bar comes from. There's also an error bar that comes from the fact that during this talk, I told you we know exactly the size of the black hole shadow. There is one free parameter, but it changes it by just a little tiny bit. And so we have this little tiny error bar that's like, essentially general relativity predicts that the size will be between this and this, right? So we have that little error bar, but it's very, very small compared to everything else. And then the other error bar that we have comes from the fact that we have this image that looks kind of like a donut, and we're trying to figure out exactly what part of that donut is the black hole shadow, right? And so the image that became really famous is actually not the only image, and is actually not the only way that we have analyzed the data. So in addition to the image that you see, there are probably thousands or even hundreds of thousands of images that were done using slightly different algorithms. And so we constrained really well any sort of uncertainties that we had in little details in that image. In addition to that, we also performed a lot of model fitting. So we had like ring shapes or crescent shapes that we fit to the data as well. And then we also compared the data to simulations. And we took all three of these methods, put them all together, and try to establish our error bar that way. And in addition to doing all of that, we also used simulations like the ones that I was showing you. And we then simulated an observation, right? So with the computer, we can simulate what our particular instrument would see, including all of the noise and all of the issues that we have. And so we can simulate an observation. We can put that same simulated data through all of the same pipelines that we use for the real data. We can measure the size of the black hole shadow in this pipeline. And then because it's simulated data, we know what the right answer is. So we can also check ourselves that way to make sure that the error bars that we are using are actually realistic, using these simulations to make sure that the correct answer in the simulation is never outside of our error bars. So we put all of that together, and that's how we get the 20% or 17%.
Great, thank you. I would say last round, one more question, perhaps? I hear a voice.
Does time stop when in a black hole? Like really close to a black hole and in a black hole, does time stop?
That is a great question. And to be completely honest, that is why I became a physicist, is that exact question. So I remember very clearly being in high school and we were learning about black holes, and I kept bothering my teacher about this. And this just kept me up at night. And the fact that black holes change time to me was just the craziest thing. And I decided that I had to understand it more, which is what led to the last 10 years of my life of studying this. So yes, but it's a bit more complicated than just stops. It's actually really interesting. So as you get closer and closer to the black hole, time will slow down, right? So the example that I like to use when I teach this is imagine you have a friend, or maybe not even a friend. There's another human, right? And so you guys are on like these little rocket jet skis is the image I have in my mind. Sorry, I do a lot of outreach with kids, right? So just pretend. So you have these little rocket jet skis, and your friend is like very confident and thinks that he can go around the black hole and not fall in. And you're like, you shouldn't do that. That's very dangerous. But he does it anyways. Okay. And so your friend goes and falls into the black hole. And you're on your little rocket jet ski and you're looking at your friend and you're like, he just stopped, right? And so the reason I'm bringing people into this is not because I actually want to, kill off imaginary people, but there's a very specific, really interesting thing that actually happens here, is that from your perspective, your friend is going to stop, right? So from your perspective, his time has stopped. And so you can wait for the rest of all eternity. You will never see your friend actually fall into the black hole. However, what's really, really interesting, because I feel like everybody tells, this is like one of those, thought experiments that gets talked about a lot. But when you actually do the math, what's really interesting is that you'll find that your friend will actually become transparent, which I think is really crazy and kind of cool. So your friend will become transparent because as your friend's time is slowing down, what's actually happening is that the time between each photon being emitted is getting longer. And so the rate that you are receiving photons from your friend is getting slower. And so you're receiving less light from them. And so they're going to like fade into nothing. However, if we flip and we instead look at your friend's perspective, from your friend's perspective, nothing happens to his time. He's going to fall in and he'll never know that his time slowed down. He'll never know that anything weird happened. I mean, he'll fall into a black hole and die. But from a time perspective, the fact that he's approaching the black hole and the fact that from your perspective his time is slowing down isn't actually going to break anything. Okay, so that's one aspect of it, the fact that it depends on who you ask, right? So that's really cool, and that's a really important concept of all of Einstein's special and general relativity theories. The other really cool aspect that I really enjoyed learning about was what happens mathematically to time. Okay, so once you cross the event horizon, if you just look at it, just look at the math, what happens is that space starts acting like time and time starts acting like space, which is super crazy and really, really mind-boggling as well. And so what's really, really cool is that you're going to be moving towards the center of that black hole in kind of the same way as you're moving through time right now, right? If you tried to stop moving through time, it's not really going to work. You're not going to be able to stop moving through time. You will still fall into the black hole.
It's almost over.
Sorry, what?
Sorry, no. Carl.
Oh, okay, sorry.
Yeah.
Oh, I didn't mute myself, excuse me.
Oh, no, you're fine.
Did it?
And so so time inside of a black hole is really crazy because it acts like space. And so maybe potentially in theory, maybe you can move through time. I don't really know. This is just mathematically what would actually happen. We might never know. There might be unicorns and pink elephants in there, right? But it's kind of cool to think about.
Well, thank you, Leah, by showing us that you're not only a terrific scientist, but a great expositor and can, relate literally everyone to your field. It's a great pleasure to have you here. As I like to say, one of the great things of IIS is our younger scientists and scholars who come here to, I would say, boost their career even further. I think for you, it's not necessary, but we are absolutely delighted to have you here, and you will stay here for a few more years. So that's terrific. And but thank you for tonight for sharing your thoughts, your view of this exciting field, and your enthusiasm. So on behalf of all of us, thank you very much, and I hope to see you back at one of these meetings, and the next one in person.
Thank you so much.
Okay, good night to all of you.
Really enjoyed
Thank
this.
you for joining us.
Terrific job. Yeah, really.
Thank you.
Scintillating.
Wonderful. Thank you.